Okay, we are going to discuss the last question on the Coulomb's law assignment, which is giving some people some trouble. It's actually not as hard as you'd think. Okay, so this is 2432, the last one. Okay, first of all, let's figure out what we're dealing with. We're dealing with an electric field pointed downwards. So I'm going to draw that in blue. This is our electric field. I use an E like this, but the book uses just a capital E, so maybe I'll try and use just a capital E. I just don't like to confuse it with energy. That's why I use this other E. But I guess in typing it's hard to do that. So I'll use a capital E here for the electric field so we can get the same answers as the sheet has. Okay, so what does this mean, first of all, before you go any further? Remember, what it means is that any charged object will be affected by this field. And remember that all fields are basically defined in the way that a positive charge would go. So that means that if a positive charge enters this field, it experiences a downward force, an electric force, which is equal to Q times the electric field, QE. Okay, that's an E there. There we go. Now, if you're a positive charge, you follow the field. But if you're a negative charge, the opposite happens. If a negative charge enters this field, negative charges do the same thing. They experience a force, an electric force, that is equal to QE, but the only difference is the direction is different. They go against the field. And here we have an electron, or an object that has the same charge as an electron, negative E, remember, E is the fundamental charge of an electron. So, in other words, it's going to experience an upward force. Okay, now these arrows I've drawn are the directions of the forces, not the direction the particle is moving. So let me erase them, now that we kind of get that in our heads. Let me erase this stuff. And let's draw a picture of what the particle is doing. So the particle, I'll draw in black, is moving this way. It's entering the field. So, and it says, so entering the field. Let me just, oh, I got the eraser on, that's why. Entering the field this way. There's the speed of the particle. And the particle, we'll draw it here, and we'll put negative E in there. Well, we'll try. There we go. So that's what's happening. So now if we draw, once the particle gets into the field, once it gets in here in the middle, it's going to have an upward force caused by the electric field, right? And a downward force caused by gravity. And so if we were to do a net force on this, we would say that we would have to look at the X and the Y. You'll notice that there is nothing forcing it sideways. So the F net X is 0. F net X is 0. But F net Y is equal to some combination of the electric force from the field and the gravity force pulling down. Okay. Now, the gravity force in this particular question, for some reason, they've ignored the gravity force. So I guess that the question makes the assumption that the mass is basically really small, nearly equal to 0. So what that means, it's negligible. So we're not going to have to consider the gravity force. The amount would be so small that it wouldn't make a difference. The reason I know this is true is because if you look at the answers, there's no G anywhere in any of those equations. So if we were to include mg here, this G would show up somewhere. So that's the first hint, the fact that They're not considering gravity, which makes your life much easier because now you've just got this situation for F net y. Okay, well, if the F net x is 0, remember, if F net x is 0, then MA in the x direction, the x is equal to 0. And of course, that means that AX has to be 0 no matter what the mass is. So that's how you get the first part of part A. The AX is equal to 0. And then if you do the AY, well, if the F net in the y direction is equal to the electric force, then MA in the y direction is equal to the electric force, which is Q times E, right? QE. And in this case, that would be an upward force. So the direction would be upward because we've already discussed how that force would work. But then you solve this for AY. And you get QE divided by M. Well, Q stands for charge, right? And it says in the question that this has the charge of an electron. So it's just E. So if you write the E here, you get that. And if you just flip those two around, you get the exact answer that the book has. So there's the AY from that equation. Now, part B, you have to figure out displacements. So in part B, let's go the horizontal displacement. The horizontal displacement, what the book or what the paper does is instead of using a D, they use an X. So the horizontal D is just called X so when you see X, it just means the distance, okay? So because horizontally the net force is 0, it's a D equals VT equation. No force, no net force, no acceleration. So X equals VT. And that's exactly what they have for part B for the horizontal. For the vertical, there is an acceleration because, as we saw, here it is, the vertical acceleration. So we need to consider if there's an acceleration, then the vertical dy will have to be this equation, the acceleration equation. And then we'll just call this y, just like they called the dy is just called y, so that's not a big deal. What's the initial vertical velocity? It's 0 because the particle is not moving up or down initially. So we get a 0, and then we substitute the AY from up here, QE over M, or if we substitute this, which is the same thing, EE over M, then you see how we have the same thing that they have on the paper. Okay? This doesn't need to be put in here because it's 0. So there's how part B works. Now part C, if you recall when we did projectiles, because this essentially is a projectile, right? The only difference is it's the electric force that's causing it to accelerate vertically rather than gravity. When we did projectiles, you'll remember that we did the horizontal and we did the vertical. And often what happened is we went blah, 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 and we got something here. We got an equation here in the vertical. And then we did this over here, and we got another equation here in the horizontal, and we had to put them together. And the way we did that was we isolated this for t. T equals whatever it comes out to. And then we substituted that t into this equation, and then we worked out something from there. That was a common strategy with projectiles, right? Isolating for t on one equation, subbing it into the other. And so if we follow that strategy, we have the horizontal, which is x equals vt, right? D equals vt. And the vertical, which comes from d equals v1t plus a half at squared, just like projectiles. And this worked out to, we called it y, and it came out to 1/2 e over m and t squared. All right, so those were our two equations, just like before when we did projectiles. They just look weird. Let's go back to the horizontal, and let's isolate for t. T is x over v. Now let's substitute that into the t for this equation. Y equals 1/2 EE over m. And then this would be x over v, squared. And then simplify. And if you mess with this a bit, you'll get y equals 1/2 EE over m multiplied by, well, x squared over v squared. And so to show that this is a function of x and y, we just kind of gloop together the things as a constant in front of the x. And we get this. And if we multiply that v squared over onto the bottom, we get this term, and then we get x squared sort of by itself. And that's the form that the answer is in. Actually, we could even go further and do it like this, EE over 2mv squared, which is probably, that's probably how I would write it, and probably how most books would write it. So this is really just a very simple formula, a very simple parabola equation, where the A value is this gunk, which came from the electric field force that was put on it. So that's how you go through that question. It's one of those, play with letters without any numbers questions. But again, these kinds of questions are very popular in university. And my daughter came home, or at least wrote home or called home many times, struggling with questions like this because they didn't do enough of them, I guess. And so here we are doing one to help you understand that sometimes you have to be able to think in terms of just generalized quantities and use equations. This is really physics. Most of what we do is math with a physics flavor, but this is what real physics is. And so this is a taste of what you'll have to do in university. You'll have to be able to do these sorts of things. But if you look at the general skeletal outline, we did nothing different. We did F net X, F net Y, and we figured them out, right? We didn't do anything different than we normally would. And then we did projectiles, horizontal, vertical expressions, just like we did in grade 11. And then we did this, which is basically dealing with the two equations together to get to here. So we did nothing beyond what we've already learned. It just looked strange because it was all letters and